This video will explain the work that has been done in the paper No Reference Image Quality Metric for NeRF, which is Neural Radiance Field Rendering in Automotive Applications. So very quickly, NeRF is a deep learning technique that can represent a 3D scene in a continuous function, and this scene is learned from some 2D images. Then, once the NeRF learned that scene, it is able to synthesize novel views from different angles for the same scene. NeRF offers a significant potential for automotive applications. However, several challenges still exist, and this paper addresses 3 of those challenges. So the challenges that are addressed in this paper are first the use of fisheye camera. So most of automotive vehicles will have fisheye cameras that will have lots of lens distortion and heavy camera models to use. And we need to use the data from those cameras in the NeRF training. The second point is that in most automotive applications, the novel view that we are interested in is usually outside of the training dataset. And the third point is that there is a need for a no reference quality metric to measure the quality of the image rendered from the NeRF with no ground truth. Here we will go into details in the first 2 points. So the first step we did is that we have integrated the automotive fisheye camera to be able to use fisheye images coming from a surround view camera system. We use the car position that is calculated by our SLAM algorithm to calculate the position of each frame. So as you can see, this is now our data set. And as you can see, the data set is taking the same path that the car has driven through, and they are all in the same plane where the car drove. So this brings us to the second point, where most of the application will need to render views from a different position. So for example, at a higher elevation or at a point where the car hasn't driven and so on. And again, this brings us to the third point, that currently all the NeRF evaluation are based on full reference metrics like SSIM, for example, and those metrics will capture a validation subset. So for example, it will capture a few frames from this data set that are, as you can see, in the same range where the car has driven, and it will use those viewpoints to render similar viewpoints or the same viewpoints and compare with the ground truth images and see how good the NeRF managed to render those views and in comparison to the ground truth. So this means that if I want to evaluate how good a model is in rendering a viewpoint that is outside of my training data set, like here, for example, where I'm adding here, there is currently no metric to measure the quality of the NeRF in that sense. To tackle this problem of evaluating novel viewpoints in the NeRF rendering, we started by using some traces from the NeRF Studio dataset. So for example, what I'm showing here is the poster trace. And as you can see again, the dataset images are within a certain range in terms of elevation, and of course there are some missing parts, like for example this viewpoint, I don't have any of the dataset in here. And what we did is that we created a novel view point camera path, the one you see in red, that is slightly elevated from the dataset range. And we first measured the traditional full reference images for the NeRF. So to have this type of comparison, we trained the same trace on NeRFacto, which is a NeRF-based model for NeRF Studio that we have been using for our experiments, and SplatFacto, which is the Gaussian splatting base model that is part of the NeRF Studio as well. We then calculated the traditional for reference quality matrix for those two models, the NeRF factor and split factor, using the validation subset. And you can see here in the numbers, the matrix are pointing towards split factor or for having a better quality. And this is actually reflected in the validation dataset. So you can see that the dataset, the rendered quality for this split factor is closer to the ground truth. What we did then is that we rendered the novel viewpoint that is slightly elevated, and we tried to compare if visually still split factor is of a better quality, which was indicated by the traditional metrics. And as you can see here, in most of the images, you see a lot of artifacts in the split factor rendered images. Even the white areas here are not as clear as the NeRF factor. So you can see here that actually the image quality for a novel view that is outside the training data set is not aligning with the measurements or the evaluation of the traditional metrics. And we have done this same experiment on a number of traces, and what we have seen is that in 33.3% of the traces there is a misalignment between the traditional matrix in terms of which model it is pointing to be of a better quality, and the visual comparison for the novel view of a slightly elevated camera path for that same trace. To tackle the problem of measuring the image quality rendered by NeRF for novel viewpoints that doesn't have ground truth, we looked over the no reference image quality metrics that are used in generative networks, like GAN, for example, and we have identified the Fréchet inception distance as a strong candidate for our use case. So what Fréchet inception distance does is that it measures the distance in the feature space using a pre-trained inception version 3 model between a set of real images and a set of generated images, and it is able to capture in the measure both the realism, like how closely the image look to the real images, how real it is, and the diversity, whether the images covers a wide variety found in real images or not. So for us, these real images could be the dataset used to train the NeRF, and the generated images could be the novel view points that are rendered from the NeRF after training. As a first step, we calculated the FID on the validation subset to see if it aligns with the other metrics, and you can see for this trace the FID actually points that the split factor is better than the NeRF factor in that case. So for FID, the lower is the better. But we have seen also that for some traces that wasn't correct, so the FID for evaluation did not align with the traditional matrix. So for that, we did visual inspection for those traces that there was misalignment, and we have seen that for those cases actually the FID aligns well with the visual inspection of the generated images. So as you can see here, for that trace the NeRF factor is actually performing better even on the validation subset. So as a total, we have found that we get 33% misalignment in terms of comparing the visual inspection of the validation subset using the traditional matrix, and 0% misalignment using the FID calculated on the validation subset. Then as a second step, we move to our target area, which is measuring the image quality of the novel view rendering without ground truth. So for that, we calculated the FID using the elevated camera path, the image generated from this camera path. And as you can see, we have seen that the FID metric is actually aligning with the visual inspection in terms of which model is performing better. So you can see here that the FID is pointing towards the NeRF to perform better in the novel view rendering, and the visual inspections align with this value as well. We have the full results in a separate video, so if you want to have a look over the visual results and the metrics calculated on all the traces that we used, you can see this video. Thank you.